And the bad news is no break. We continue. So the main focus of this lecture is public key infrastructure, but I promised you yesterday I would say something about Signal. And actually there is a connection to PKI because we see here the problem of the Signal protocol and that we need to authenticate public keys. So I guess I asked yesterday, many of you are using WhatsApp or Signal or Facebook Messenger or Skype. So I think it's one of the great contributions. We already discussed yesterday that Diffie-Hellman is expensive compared to what we had before, just RSA. But then Diffie-Hellman gives us better features. And in fact, for those of you around long enough in the 90s and in the knots, we tried to get email encryption sorted out. Anybody encrypts their email here? Yeah, a few nerds managed to do it. I sometimes do it for projects, but on average, this is a big failure. It's kind of amazing. It's very hard to use. We didn't manage, but somehow, for messaging, we managed to solve the problem. SMS is not secure, but for messaging, somehow it's being solved. And it's also part of the debate or the discussion tomorrow. I will talk about law enforcement. They're now complaining they actually can't read any more the messages because, in fact, there is too much encryption. So the Signal protocol was designed by Moxie Marlinspike and Trevor Perrin. They started working on this about 10 years ago. It took them several years, and there is many versions of this. I'll describe here a version that's published in a paper and analyzed in a paper, of which I give you the reference later. But it may be that there is still new variants. It's an evolving protocol. It offers forward secrecy, which means if you compromise a phone today, even if you intercept all past communications of this phone, you will not be able to read the messages. It also has an interesting other feature called, a new feature introduced by this protocol called post-compromise security. This means if you, say, go at the border and they take your machine and they take all information, in fact, if you then reactivate the protocol, run it again, and they intercept communication, they can't read it. Unless, of course, they put malware on your device to intercept all messages, but at least from the protocol, from the keys they got now, you actually keep refreshing your keys. And that makes the protocol quite complex. So simple, what we tried to do with email was give everybody a public key and a private key to encrypt and a public and a private key to sign. Just two keys. And it didn't work. Amazingly, this protocol is much more complex, but it actually works. I will not fully give the whole detail because that's an hour lecture, but I'll give you some feel. So in fact, there is 3 levels of public keys. Okay, long-term public keys, medium-term public keys, and one-time public keys. In addition, there is ephemeral public keys. So in fact, there is like 4 types of public keys only in this protocol. And then there is also 3 symmetric key chains. So there is again a system of 3 kind of symmetric keys, and for every message the keys change again. So it gives you an idea of the complexity. Also hard to analyze and hard to implement, but apparently we now have a secure system. So more or less if you join Signal or WhatsApp, what happens is you send your long-term public key, and I note this in green, and the L is for long-term, and the M is for medium, and then you also make your one-time public keys, and of course you keep the private keys private. What you do is you also sign with your long-term private key, you sign your medium-term public key, okay? And then you send all the other public keys to the server, and of course Bob does the same thing. And if now Alice wants to talk to Bob, so she wants to establish contact, then actually the server will send some information over, namely more or less the long-term public key from Bob, the medium-term public key, which you can check with the long-term key because it's signed. So you only have to check the long-term public key. And we'll come back to how you can do this. And then you send the first one-time public key of Bob. And what Alice does is she makes another public key. So this is the ephemeral key, which is written here as small x1 and capital X1. So this is all the curve setting. So this is the multiple of the point x1 on the curve, and this is then the point on the curve, x1 times the base point. Or if you would think in Diffie-Hellman terms, this is x1 and this is alpha to the power x1 mod p. And then, based on this, both parties compute the root key, and more or less it's a mix of kind of Diffie-Hellman keys. So every time it's a Diffie-Hellman key exchange, again elliptic curve notation, So in elliptic element will be alpha to the x to the y. In elliptic curve is x times y times the point P. And so as you see, you have the medium-term key of Bob with the long-term key of Alice, the ephemeral keys of Alice with the long-term, the medium key, and the one-time key of Bob. And here, of course, Bob has the corresponding private keys, and he can manage this. So all these keys are different, and they all have a different goal in analyzing the protocol and making it robust. So it actually costs 4 Diffie-Hellmans on each side. So it's much more complex than a simple Diffie-Hellman. But in the analysis, all these things play a role to make sure you defend against all these kinds of attacks. And it would take actually an hour lecture to say if we leave diff one out, what is the impact? If we lab one out, what is the impact? So in fact, it's a very sophisticated protocol, but studying it requires quite some time, probably an hour, before you understand why all these things are there. But it's not that the designers just put some things on a pile and say, let's make it more complex. In fact, there is a strategy behind this, and it's needed to prove it secure. So I guess it all comes down to how do you know what the public key of Alice is the long-term public key, and of course there, this is a screenshot, of course you get as a user, you get the QR code or you get this 60-digit code, and you're supposed to check this. I guess we all do that, right? Sure. Of course we don't, that's the problem. That means that actually, if you don't check it with the person you're talking to, you actually never know when you're talking to the NSA, and the NSA actually sat in between or compromised WhatsApp and gave you the wrong public key. But that is, if you're paranoid and you really want to do it, you can actually check with your friends. You can display this in Signal or in WhatsApp, and you can actually check that you really got the same long-term public key. And remember, this is used to authenticate the medium-term public key. And then that's enough to actually know who you're talking to. And then to get robustness, you have all these one-time public keys and all these ephemeral public keys. So from that perspective, the protocol is actually quite simple. It's of course a big mess in the sense that why do we have so many things? But then all these things are actually just Diffie-Hellman exchanges with different kind of keys. That's the bottom line. So now the symmetric keys. So symmetric keys, their simple protocol introduces something called the double ratchet. And I guess you all know what a ratchet is, so you try to kind of lift yourself up. And so this is mostly for forward secrecy and post-compromise security. So what you do is you actually have sending keys and receiving keys. And then you also have, as we will see, a root key chain. So you have 3 symmetric key chains. And every time you use a key, you will actually update the key. So every time you got a message from Bob, you decrypted it, you can actually decrypt it with that key and then update the key. So if you compromise a device, you can no longer find the key. Of course, this assumes you don't store your messages on your device because then there is no point in destroying the key. Or if you take a backup in iCloud, of course, then again, you're vulnerable. But if you have this disappearing feature, you switch that your message is deleted. In fact, Signal or WhatsApp will immediately delete all the keys. Okay, so every time you have this, in this case, I took a key from the sending key chain. So you have a key derivation function, which is kind of a MAC algorithm. It's a one-way function. So you apply a one-way function, and you get the new state, and you output a key. And every time you receive a message and you read it, or you send a message, you actually update this chain. And so if you compromise a device, at this stage, you will never be able to go back and find what those keys were. So this gives the robustness. Without having to use fancy cryptography, you just keep hashing your key all the time. Of course, that only works because you have this kind of messaging system where you know, I now got the next message. And that's the problem of email. Email, you can't do this because you can't keep hashing your key and then you suddenly get an old email back. Oh, oops, I hashed my key, and you can no longer decrypt this. So this is why the setting of messaging seems very similar to email, but the subtle difference that you actually have some kind of server that keeps track of what you received is enough to actually allow you to hash your keys and make the system much more robust. And in fact, much easier to use. You don't have to know all this stuff to use Signal or WhatsApp, right? It's just all behind the scenes. While the problem of email security is it was a mess for users to deal with all the keys. Okay, so what happens here, indeed, if a message key is compromised, and you'll find out right away why they're numbered so strangely, once this one is compromised, you can never get back to those. But of course, there is still a problem if your device gets looked at the border, and they ask you to log in, and they actually get the state and this key, then of course they can compute all future keys. And so this is called one ratchet. This is one of the ratchets, but there is actually a double ratchet. This is why the Signal protocol is called double ratchet protocol. because there is a second ratchet. And the second ratchet is very simple. It's to make to build a root key chain. So I told you there is 3 key chains. In the previous slide, I showed you the sending key. And I was a bit lazy. I should also have the same chain for the receiving keys. But there is actually, both are generated from the root key chain. And this root key chain is very similar. It again updates keys and produces alternately a sending key and a receiving key. Okay. But the real clever trick is that every time you also do a new Diffie-Hellman. So every time you send a message, you send a new alpha to the x, or in elliptic curve terms, a new x1 times p. So a secret times the point, the base point, that gives you a point on the curve. And so every time you do this, you actually send as Alice a new capital X, and Bob and every time generates a new key as well. And so you build a Diffie-Hellman key, Alice as her secret key, my Bob times Bob public key, and Bob, of course, as Alice's public key times Bob's secret key. And so every time you do another update, so the first time your thing is running, Alice and Bob each send a new public key, and then you compute the Diffie-Hellman key 1, which is key number 1 of Alice and key number 1 of Bob. And then in the next step, you introduce key number 1 of Alice, and Bob makes his new key, so then we have Diffie-Hellman key 1, 2. And then Alice's turn again, she actually makes key 2, 2, and so you can now see why these things are numbered. So in fact, you do continuously Diffie-Hellman. Every time you send a message, you also send a Diffie-Hellman component. And this is then used in the root key to keep updating this. Okay? And what is now so nice is that even if this here is compromised at this stage, so you're at the border and they take the whole state of your device, what's going to happen next time is you're going to get a new Diffie-Hellman key with a new component in there, which in fact these guys could not foresee, so they will actually not know what the next key is. So very quickly you will recover your state and you'll be robust against attacks again. So no matter what happens at this stage, your past will be secure, and also very quickly your future will recover security. So this is kind of the most robust protocol you can make. So overall it's a bit complex, of course. So you have this setup with these 4 Diffie-Hellmans to make root keys, and then you have the root key chain where every time a Diffie-Hellman is used, and then those produce the starting points of the sending keys and the receiving keys on the previous slide. So maybe I should make one slide where all the chains are on there, but more or less the bottom line here, these are the starting points of the chains. On this slide, I only draw the sending keys, but there is also another chain for the receiving keys. So it's a bit complex, but in fact, there has been an analysis, and that actually shows that this protocol indeed satisfies these properties, and formalizing these things is not so easy. That's where I want to wrap up the Python protocols. So of course, you can stare at the protocol. It's very important that you try to define what security is. And if you speak to cryptographers, they will even disagree in which model you should define security. And it's not surprising that you have a paper, for example, discussing the signal protocol. The definition of what is secure, what is the goal, takes several pages. To really formally define what it means for a protocol to be secure takes several pages. And then to prove it's secure actually can take dozens of pages. And sometimes even people have bugs in those proofs. So this is actually a very hard problem. But there is a lot of research and a lot of smart people are working on this. I mean, in the past decades, we made lots of progress. So of course, you can look ad hoc at things and find flaws. These are things, for example, Matti is very good at. He looks at this clever protocol and he looks at the proofs, but he still finds flaws anyway. Right? In spite of the fact that there is proof, sometimes the things don't fit together. Of course, you can use information theory, but this is very rare. There is lots of work in cryptography. Most papers use complexity theory. They try to actually formally define things, and also they work in certain models in which they can prove that if you combine multiple protocols, then in fact the result is still secure, which is not obvious, as you've seen in Matti's talk. So one model to avoid these things is called universal composability, but it's kind of difficult to prove your protocol secure in this. And then there is a parallel track of research in formal methods, people who have been historically working on proving correctness of programs, a very hard problem. Right? And their tools have been actually used more and more to actually prove protocols secure. And so Tamarin is one of those tools that can actually prove your protocol secure. Of course, to use Tamarin, you have to be an expert already. There is also tools like ProVerif, which are easy to use, but they only test for flaws. They're very easy to learn to use. So we have an expert here, and more or less the students in one session, they can learn how to work with it. It doesn't prove your protocol secure, but in fact, you can check it quickly for some flaws. But becoming a tamarin expert, that's a different business. For this, you probably need a few months to do this. And again, where the state of the art is, in TLS, for example, during the TLS standardization 1.3, so after Snowden documents, it was decided to clean up TLS. Academics worked together with industry to analyze many versions. And in the end, a team at INRIA managed to actually prove the protocol secure, but also produce code that was provably equivalent with the protocol. And that was also possible for a while, but now this code is only 20% slower than handwritten, the best handwritten optimized code. This is a very, very impressive breakthrough that happened a few years ago. And for example, Firefox uses this code. So that means that you're kind of almost sure that there is no bugs in your code, that your code implements the protocol, and that your protocol has no bugs. So this is an enormous development. 30 years ago was unthinkable, and is possible today. But of course, this is still a research topic. For example, this has not been achieved for the signal protocol yet. TLS is much simpler, actually, than the signal protocol. But I guess that's the good news, that we are making a lot of progress, and it's not all work by hand. So, but the properties are subtle, and I think Matty's talk was a very good illustration of this. Use the standards, because IETF and ISO do a lot of work to get these protocols correct, and also IEEE. It takes a long time. And I guess the most important rule is rule number 1 of protocol design: don't. Okay? So most people know that they shouldn't design their own block cipher anymore, unless they want to do a PhD. It's the same thing with protocols. If you really want to design your own protocol, do a PhD in protocol design and then make your protocol. But many of the problems that happen in IEEE Wi-Fi, for example, is people who actually don't have qualifications start hacking together a protocol, and then it takes years and years to clean this up. But so that's the most important thing you should learn today is don't design your own protocol, just like you don't design your own crypto. It's just too hard. So when discussing the signal protocol, we already discussed this problem of public keys. So in the end, of course, Signal or WhatsApp is fantastic, or SSH, but if you don't check the public key of the other party, well, then there is no assurances. Now, so cryptography in the end boils down to how do we get each other's public keys? And that seems like an easy problem, right? Because it's a lot easier than agreeing secret keys like you have to do for GSM or 3G or 4G or 5G. The operator has to agree on a key with every user, or also in your bank card. There is a secret key with every user, and this is really a nightmare to manage because, of course, the bank has to have a copy of this. So you would think that making or distributing public keys is a lot easier. And so this was research done in the 90s, and some people made quite some money with this stuff. The hype was not as big as cryptocurrencies, but there were also companies with big valuations of billions of dollars in this business. So how do you distribute public keys? It seems like an easy problem. And of course, we use CAs today. I guess you all understand CAs. Most of you will know it. I will just wrap it up. And one problem is we have too many CAs, or everybody wants to be their own CA. And also, as we will see, regulators intervene with CAs. But so, in principle, you could distribute your key point to point, like on your business card, as cryptographers used to do, but we no longer have business cards. So now you can have a QR code, or you have this system of WhatsApp or Signal, where you can actually check with your friends what their public key is. Of course, you shouldn't send this public key over WhatsApp, right? I hope you all understand that. That does not solve the problem. So you have to find another channel to send your public key. I think at some moment there was really this belief, and some of you are too young to know this, but I think until 25 years ago, the telco companies would dump every day in your every year in letterbox a phone book with phone numbers and names. I don't know, some people have never seen those things. But so that was what happened. And the idea was maybe we should do the same thing with public keys. You know, the phone company will print the public keys of everybody and the names, and then we'll distribute this. Well, maybe printing is a bit of a problem because these phone books were very thick for 7 or 8 digits per person, so maybe you want to do it digitally, but why don't you issue just a list of all public keys? And I guess the biggest answer there is, of course, privacy. If you do it digitally, then suddenly all the information of everybody becomes available, so you can't actually do this, apart from the fact that what is a public key is not correct, and we'll come back to this. So what you would do today, I think if you would start from scratch, you just say, oh, this is very easy. We make a service somewhere, and if I want somebody's public key, I just ask them, hey, what is Alice's public key? And then they give me the answer. That's what you would do today. There is some problems with this. The first problem is, do you pay for this service? So do you charge? If not, I can flood them with requests, and then if they don't charge me money, they will go out of business. The other problem, again, is privacy. Then I can find out whether somebody exists in the system with this name, and maybe I also have to get email address and more details, so it's a privacy issue. And of course, it assumes that everybody is online, which was not the case when these things were conceived. So, in fact, the modern PKI, the concept of certificate, was conceived by a student of Rivest in 1978. And I can tell you, 1978, computers barely talked to each other. There was the beginning of the internet. The TCP/IP had not been made universal, and there were the first modems at 2 kilobits per second. So the idea of everybody being online all the time was actually absurd at the time, so you had to have a system that would work offline. So what actually was coined by a Rivest student was certificates, and then the company Entrust Technologies in the mid-90s coined the term public key infrastructure. We'll come back to this. Also, people have had many brilliant ideas, like what if somebody's name is their public key? Wouldn't that be fantastic that your name is your public key or your email address? Okay, that's called identity-based cryptography. And in fact, using pairings, I think Frederick spoke about pairings yesterday, you can actually get identity-based cryptography. That sounds a fantastic idea. Until you start thinking about this, so if my name is my public key, how can I compute my private key? If I can do it, anybody can do it, right? So in fact, the only way this can work is that a central party computes all private keys for you. Now you can see why some government love this idea, that your name is your public key, and then they will compute your private key and they will give it to you. Right? It makes all the key management go away, but they just have all the keys because they can compute them. So it actually didn't quite fly because there is some problems there. Of course, you could give the keys, you could share it over multiple governments with thresholds or multiple agencies to make it more robust, but still, it actually never happened. And then the other problem is, what if you lose your private key, you're sloppy, and your private key is lost, then you have to change your name, which is really annoying. Right? So in fact, this sounds like a fantastic idea. I will not give you names, but I know academics who made companies and made lots of money by selling this idea, but if you start thinking about it, it's really a crazy idea. Right? It actually doesn't work, but it sounds very cool. So what works, of course, is certificates. I assume you all know about this. A certificate, more or less, as cryptographers, we shift the problem once again to another key. Namely, we have a CA, but we'll sign with this private key my name and my public key and the validity period. And so you link a name to a public key. How do you check this? Well, with the public key of the CA. And how do you find that one? Well, that's the ultimate solution. You shift all problems to knowing the public key of a CA. That should be easy, right? Yeah, it would be easy if there was one CA. The problem is today we have thousands of CAs. And if you look in banks or large companies, and these things have been around now for 25 years. So in banks make an inventory, they find all kinds of engineers who actually created their own CAs, because since 2000, Windows software has the full CA software included. And so banks keep finding engineers who somehow created CAs and were starting issuing certificates with private keys in there and so on. And then it's actually a big problem that it's too easy to actually be CA. And then the question is, what if you want to revoke things? What if somebody leaves the company or lost their private key? Well, the philosophy was to have certificate revocation lists. So say every day you publish a list of revoked certificates. It's a bit like credit card numbers. In the 80s, the shops had lists of stolen credit card numbers, and before they would accept the payment, they would look in the list whether the number was there. It's kind of a simple mechanism, and again, you sign this with the private key of the CA and you make it public every day. Does this work well? Yeah, sort of. There is scale problems. For example, in Belgium, when we designed the ID card, the government decided that we would always issue cards, but as a citizen, you could choose not to activate the card. And the only way to do this in an easy way was to revoke this card. So this meant that in Belgium, very quickly, we had 8 million cards and 2 million cards revoked. So this meant that the CRL list was actually several tens of megabytes, which today is okay, but of course in 2004 this was a major problem. At the internet speeds and the mobile speeds available, it actually is not so easy to deal with it. So what is PKI about? So PKI is about managing keys and lifecycle. We look at what's in there and how these things can work together. I guess any cryptography needs generation of keys. You have devices for this. You need certification, get a certificate. Then you use your key, and then the certificate will be validated every time you use it. And then your key will expire, and you have to get a new key. And ideally, this should all work without the user actually being involved, because you know what do users know. It actually should all happen in a transparent way. It's a bit like it's in WhatsApp or Signal. The users don't know that there actually are 3 levels of public keys with ephemeral public keys and whatever. And that is always Diffie-Hellman happening. So the idea of PKI was to create this infrastructure behind the scenes, build it in the IT systems, and have a service for keys in a very transparent way. And so they have this done for all applications. So this should be a service. This was envisaged. And so these companies that went to the stock market in the late 90s, they actually said, we're going to manage this, and we're going to have one PKI, your infrastructure, just like you have internet and you have water, electricity, you just have a key service. And that will do, of course, your web, your email. People still thought they were going to protect email. They still believed that. They didn't know it was impossible. Desktop security, your enterprise resource planning, and your VPNs. And so the idea was buy our PKI and we will secure everything. Of course, we now know that's never happened. These are actually real slides from Entrust from the late 90s. So, of course, what happened is we got the web PKI. We never got email security. We have WhatsApp, but that doesn't use PKI. That just uses QR codes. We have, of course, in your desktop, you have PKI, but it's mostly used only for code updates. And like Active Directory is still using cabrals. It's not using public keys. And VPNs, I guess PKI is there also the pain, right? I know that many organizations still use manual key management or symmetric keys because it's just too hard to deal with the VPNs. So at the core of a PKI is a certification authority. That's an authority that actually signs certificates. So you give it a certificate and it will sign it. It's a very simple technology. As I said, from Windows 2000 onwards, it was on everybody's machine. If you take your Windows box, it's actually in there, all this software to do this. But of course, if you do it seriously, you want to actually have this in a bunker with probably an HSM with your keys. And you want to have guys with dogs and guns around it because, you know, if you breach this, you actually have a problem. So you actually want big security. By the way, I think I visited 2 CAs already. I don't know what these companies did, but I've been 2 companies let me in to go to their CA and look at their HSM. Very cool if you can ever convince a company to do that. Very cool to do that, but it's not easy. But that's more or less what you do. And so you, of course, what you really need is not technology. What you really need is lawyers that say what it means to sign something. And this PKI infrastructure now exists for 30 years. Has anybody ever heard of a CA being sued for actually signing the wrong thing? Did they ever sign the wrong thing? Many times, but they've never been sued. And why not? Because there is a document that's 80 pages written by lawyers that says we're going to charge you money for a service. The service will suck, but you will pay anyway. And if something goes wrong, we're not responsible. That's more or less a summary of the 80 pages. And people made a lot of money to draft those things. Nobody reads them. And that's the reality that, in fact, you produce these statements, but you never take any liability. And we've seen many cases. Well, I guess there is one case where the company went out of business, right? That's the worst that ever happened to a CA. Is they went out of business. You also have to store certificates. This is now less of a problem than before, but in the 90s it was a problem because actually in the late 80s, the telcos still had a monopoly and they actually had something like email called X400. It was very similar to email. There was just one difference, it didn't work. I had X400 addresses, it didn't work. You couldn't send attachments. It was very painful to use, but that was the telco's idea of having email, was X400, and then their phone book was X500. That was the directory service. And then the certificates actually were standardized by the telcos in X509. And this is a very famous standard, and unfortunately we're still using this. It's a big pain. It was updated a few times. We're now at version 3, and it never got better. It's a big mess. It's a very complex standard, and verifying X509 certificates is kind of a pain, right? But also, because they had the monopoly, they also had the X500 protocol to actually implement the directory, but that didn't work. It was also, just like X400, the X500 didn't work very well. So in the end, people invented LDAP, and LDAP stands for Lightweight Directory Access Protocol. So this is the heavyweight one that doesn't work, and this is why the lightweight was invented. So if you wonder why LDAP is called LDAP, because X500 sucks, that's the reason. Okay. So you have to revoke certificates, of course, because people leave your organization. People in Belgium lose their ID card, or they lose their ID card with their PIN on it, or your machine is compromised, or even worse, your CA is compromised and you want to revoke certificates. That's a big problem. And in general, this is a hard problem to deal with. Issuing certificates is easy, but revoking them is hard. Right? Think about it. It's the same thing. If you lose your bank card, what do you have to do? Well, there is this number you can call, and you have then to block your bank card. But how will they check it's you? Right? In Belgium, you can actually have some identity data, but in general, if somebody lost their wallet, how will you check who they are? You say, give me your identity card number. No, but I lost my wallet. Give me your bank account number. I don't know it by heart. Give me your name, but anybody can say your name. So this is actually a big problem in practice. How do you make sure that this is the real person revoking this and not somebody playing a prank or trying to bring down your service? So, and of course, you can't do this offline. You have to do this in real time. So in general, there is mechanisms indicating valid certificates, and this is, as we will see, the new trend. So more or less in the last 10 years, people have actually said, well, we're just going to say what we issued, and revocation, the hell with it. It's too hard. We're not going to do that anymore. That costs too much money. It's too complex. Is there problems? Yes, but they're not our problems. We just put it in our statement. We don't do this, and then it's your problem. Of course, the CRL mechanisms is indicating invalid certificates. I explained to you the problem of CRLs, the scalability, the fact that they become very big. But then there is many tricks like delta CRLs, segmented CRLs, where you try to split them up in smaller pieces to make it more efficient. And that kind of works. That's not a problem. And then what you really want is proof of status. And what we there have is OCSP, and we've seen some usage of this. There were other ideas, but they actually never flew. So OCSP has seen some deployment. The main problem there is you offer a service, and people don't want to pay for it. So you have to answer requests. That takes you money and time and bandwidth, and you have to have a high availability server, but nobody wants to pay for it. So that's not a very good business model. The CA model is a very good business model. Why did these companies get billion-dollar valuations? Because they went to the investors and they say, look, we're going to build this bunker, we're going to put an HSM in there, and then the guy with the dogs and the guns, and our budget is $2 million per year. You can run a CA for $2 million per year, right? Okay, you have to rent your bunker and so on, and you have to have some CEO that goes and gives talks and so on, but that's about the cost, €2 million per year. What is our income? Well, there is millions of companies on the internet. We're going to charge them €10,000 to sign a certificate, and will be valid for 1 year. So if I have 1 million customers, it's only a very small share of the market, 1 million customers, and I charge them $10,000 per year for a certificate, I will make $10 billion per year. That's my income, and my expenses is only $2 million per year. So you can imagine that the stock market bought this, and these companies got enormous valuations. It's still a credible story, because the real story they said is there will be 1 billion of users on the internet, we're going to charge them all $50 per year for a certificate. We're going to make $50 billion per year. Anybody here ever paid for a certificate for themselves? So that was a crazy business model, and this is why these companies had crazy valuations. But okay, so that's the cheap part. Of course, doing revocation is expensive because then you need a hotline 24/7. You have to authenticate your users and you have to make sure that you issue those things. That actually costs money, but that was often dropped. So CRLs, as I said, are simple. You can do this automatically. It's not a problem. And there is all these tricks to make them more efficient. The only problem was, of course, that like many PKI things, all the vendors had their own implementation, and they made sure that certificate from vendor A could not be understood by vendor B and vice versa, in spite of the fact that there is standards, and there is all these extensions in X509 version 3, which make sure that all the vendors protected their market share. And so you should remember that this PKI hype started around 96, 97. .com crash came in 2000. Okay, what happens in 2001? One of the big CA companies, VeriSign, issues 2 certificates to fake Microsoft employees. Oops. They can now sign any code or software or systems for Microsoft. Oh, that's easy. We're just going to revoke those certificates. It turned out that Internet Explorer, I hope you still know what it is. It was the browser of Microsoft before they had Edge. Was the most widely used browser. Did not do revocation checking. So Microsoft actually never even bothered to implement revocation because that's too slow, right? You want to visit the website, you first have to find out where the CRL is, then download the CRL, then look up in it, whether the certificate is in there, and then say no. So Microsoft never even bothered to implement CRL checking. So there was a big problem because VeriSign revoked the certificates, but the Microsoft software didn't check for it. Because who said you should check for those things? So a lot of security in the beginning of PKI was security theater. So you actually had a lot of show, but in fact you didn't implement anything because you would not have anything that would slow down your system. And of course, to be fair, the internet was slower than today and things were, performance was an issue. And so this is why many things were not implemented. So OCSP came a bit later. So your online check, it actually makes sense. So you send a query to the CA or some other organization that's assigned by the CA, and you send a hash of the public key of the CA, so you know it goes to the right entity. You send the hash of the public key in the certificate and the serial number. So this is for privacy reasons. You don't send personal data, you just send hashes of public keys. Of course, it's not perfect privacy, but at least you don't start broadcasting names of certificates you're checking. And then what you get is an answer which says the certificate is good, is not revoked, or it's revoked, or we don't know. And you also get some information on how fresh this information is. So when did we last get info from the CA? When will you get next input? And when did we actually produce this? And the statement will be signed. So you get more or less a proof that you checked something. So it's kind of good because you get the status of a certificate. You actually, and again, there is a performance problem because what happens is if you visit the website, you get a certificate from the website. Now you have to check for OCSP, so you do a query, you get the response. Again, that slows down your web visiting. So to actually speed things up, stapling was invented, which means the web server themselves would ask for the status and then send it along already with certificate. Of course, that means that it's not as fresh, right? And if you take over the website and you hack it, you're going to send an old response back, right? And say, this is the most recent I have. And you will actually get less security as well, but it's kind of performance trumps security. Of course, you have to be online, which is not a problem today, but it's not always possible. And of course, there is this, if you give OCSP responses, there is this problem, you can be DDoSed. And in fact, you can't charge for it. If you charge for this stuff, people will say, what is this? Right? So you have to kind of calculate this in your pricing model that you will give answer so many requests and not more. So what some people did was, some organizations, is that they actually were issuing OCSP answers, but they were basing them on a CRL, which was a day old. Because that was cheaper again. So you issue a CRL, and then you issue some software that looks in the CRL from the last 24 hours and gives the answer. So you get a very recent status update from information of 23 hours ago, which is, again, not really what you want. So more or less what you also see, especially in the browser ecosystem, is what happens if you get no answer. So you get a certificate, you visit the website, you get a certificate of the website, and then you do an OCSP request, and then you get no answer. What do? Well, the browser continues. Okay, that's what it does, because it's always availability and service before security. And anyway, as a user, imagine that this browser would block you and say, oh, I can't show you this website, it's not secure because there is no OCSP answer. What will you do? You will switch browsers. You will see whether maybe Firefox will do it or Chrome will do it, or that's what you're going to do as a user, right? If you can't get to the website with one browser, you'll try the other one to see maybe this one will do it without OCSP. So, in fact, this is a while ago, but I think about 10 years ago, Firefox made an option in which you could tell Firefox to stop, actually, if there was no OCSP answer. And just to see what happened, I clicked this box, and I couldn't use any server at the time of the university anymore, because none of the OCSP provider of the university never gave an answer. So I couldn't do my job, more or less. So a lot of books and papers and standards have been written about revocation, but it's something that's actually difficult to implement. It costs money, and it's hard to do. And I remember that in the late 90s, I did quite some audits of CAs, because at that moment, the consulting companies had no idea what a CA was. And the banks needed an audit report, so then they called the big 5 company. There were still 5 at the time, and then they say, what is this CA? And then let's get this professor there, and he will look at stuff. I saw amazing things. For example, I will not give you the bank, but I know a bank where I said, and where is the root key of the CA? And then we went to a desk, and a developer of 22 years old to open this drawer, and out of lots of things, here, he said. I'm not giving you the bank name, but it really happened. So my memoirs. That's what happened, because the banks had no idea what this internet stuff was and what all these things were. That was the reality of this world. I guess it's now, of course, much better, but this is how things were in the Wild West in the late 90s. And so I guess it's still a very challenging thing to do. And another question which I would ask is, what are you going to do if your CA is compromised? And then there was silence in the room. And then somebody said, this will never happen. And I think even today, if you go to a bank and you ask this question, they will give you the same answer. They say, that will never happen. It's just unthinkable. We actually saw a case. DigiNotar, CA was compromised. What happened was that the company went out of business, and all the browsers had to issue a new version of their browser. That was happening, okay? So I guess that for a CA, it's even worse, but I guess if it's an internal CA, you can probably deal with it with an emergency procedure, but if it's a CA at the web level, you don't want to know. You want to tell them automated key update? I will not say too much about this, but again, users should not know about this stuff. It should all be transparent. We should follow the model of Signal or the Signal protocol, where everything changes all the time and the users don't notice anything. Again, a very common thing which was done in the past was that your certificate would expire, and then they would just issue a new certificate with the old key, because that's the easiest thing to do, right? And everything, you're sure everything will keep working. Okay. Backup and recovery. I think this debate is now a little bit less political, but it was very political in the late 90s, 2000s. So of course, if you encrypt your company data, employees do this, then you somehow want to have a backup copy of their private keys. Because if they get hit by a bus and you lose their private key, well, what are you going to do? So you have to have a copy of the key, okay? So in case they leave or something unfortunate happens. But of course, you want to do this in company control, and you want to have typically a 4 eyes principle and logging and whatever. You don't want somebody to just start doing this because you have a big problem. Signing keys, you can argue you don't need backups. For signing keys, you can just issue a new one and keep the old certificate, public key, but the private key you don't need to do again. But of course, as we will discuss tomorrow, governments actually said, you know what, all this key management, this is difficult, why don't you give us a copy of the key? Okay? And then we'll make sure that you never lose it, because we're very good at storing stuff, so with archives, we will make sure we do this. Of course, the real thing what governments was access to keys for communications, not for storage. If they want data stored in your company, just come with a warrant and they get the data. But for communications, they actually wanted keys, and so they advocated that governments would keep backups of keys that actually nobody needs to back up. But that made this topic quite sensitive. And for example, this is again going back in history, but in 1999 we got the signature directive. And this actually is kind of surprising now, but this was Europe intervening, and not because they wanted to change the market, but they were mostly worried that governments in France and UK would actually enforce the use of CAs that would ask copies of all users' keys. So they were worried that CAs would be used as a center of control. If you don't give us user keys, we will not give you a license to operate. And so the EU actually did good things there. They intervened and said, you can't actually do this. You cannot impose any rules on CAs, which in retrospect was a big mistake. How we got DigiNotar. But the intention was good. The intention was, look, governments, you can't use the CA model to get copies of everybody's keys because you don't need them. Then you have non-repudiation. What can we say about this? Well, it also needs timestamping, actually. And this is very easy to explain, that you actually need timestamping. And it's amazing that, for example, there was ISO standards being written. We had actually a project called TimeSec, funded by the federal government. And this is a remarkable project. I was running this project, and we wrote some deliverables. And one of those is actually cited in the Bitcoin paper. So some of the ideas developed at the time actually are very related to blockchain. But in fact, everybody knew that you need this because it's a very simple example. So imagine you're signing documents with your ID card. So you sign a document today, and tomorrow your private key is stolen. Okay, so it's clear that actually this signature is valid because you signed today and the theft is tomorrow. If you have the opposite scenario where your key is stolen today, and tomorrow the signature shows up, this is not a valid signature. You actually want to revoke your key. So this actually, you should be able to, a signature here should not be valid because it was made after the key was reported stolen. This is very easy to see. So I guess what we have to do is put the time of signing in the message, right? Then it's solved. Of course not, because the bad guy will put the time of yesterday in the message. So in fact, you have to have an external service registering your signature to prove it existed before the revocation. Okay? And so this is, you all understand this in 5 minutes. Do you think that people issued timestamps or timestamp services? They never made any money. So in fact, the company by Stuart Haber and Mike Stonetto invented the timestamping protocols and the first hash chain. It actually, Shorty Technologies, they never made any money. And even in the blockchain hype, they're still not making money. They should have changed their name to Blockchain Technologies or something. But so in fact, it's kind of a full denial of the industry. Everybody understands we need this, but nobody does this. Why? Because it's a pain and nobody wants to pay for it, right? Do you want to pay 10 cents every time you sign something to just get somebody else to give you a assigned time? Of course not. So skip the application software. Integration with application was a big problem. So in the end, this never happened. So we got the PKI for the web, and we got some PKI for code signing. And then, of course, the banks got PKIs in every one of their corners they don't know about. But for the rest, we got the big EMV PKI, of course, the biggest one. But it's a very complex system. And so what sounds like a very easy concept, just 2 slides, if you start looking at it, actually it's a very complex system to manage. And you do need, in practice, to run all this, at least 10 people, because they have to be available, they have to have expertise in HSMs, in cryptography, in all these protocols. It's actually, it sounds very easy, but in practice it's very complex. And especially scale is complex. So most standards are CCITT, but then IETF made profiles, which means they simplified them. And so they actually were driving the market on the internet mostly, so these are available, like certificate profiles, CRL profiles, management protocols. A few things about trust models, very quickly. So this is what the model was envisaged by CCITT. more or less that you have a root CA, here are the users, and the users would all trust the root CA, and the root CA would sign your public keys. That's a very simple model. Of course, the world doesn't work like this, because CCITT was based on a country, so they realized that CCITT would sign the public key of Deutsche Telekom, or of, at that time it was called RTT, still in Belgium, and then they would sign user keys, because you can't request that everybody goes to Geneva to get their certificate signed or talks to Geneva. So this is the hierarchy model. We still all trust, or the vision was, we still all trust CCITT, or the central authority. There is one public key you have to trust, and then you can check things. So the only place where it really happened is the credit card system. So in fact, you trust the MasterCard and the Visa and the Amex logo, and they sign the public key of the banks, and they sign the public key of the users. But the rules are made by Visa. Visa will say how many dogs you need and how many meters of concrete, and they will impose the rules on your CA and on your certificate policies. They will impose that to the banks, and then you can use the logo, but in fact the users and the merchants, they actually trust the Visa logo. And Visa makes the rules in the system. In the browsers, it was very different, because of course some people had the brilliant idea, I will make a CA, and I explained you their business model. So cost of 2 million, income from companies 1 billion, incomes from users tens of billions. Okay, so once you sell such a business model, there is immediately, like with the cryptocurrencies, dozens of people do the same thing. And some made a lot of money. At some moment there were 1,000 CAs. And then all these CAs actually went to the browser companies and say, put our key in your browser. Because if you visit a website, say Amazon.com, how do you know whether their CA is VeriSign or Torte or Global Sign? How do you know? You actually don't know. So in fact, all the CAs that have been approved by the browsers, and the browsers play a very strong role there, they vet CAs, and so they actually include their public key in your browser. And then if you use a browser, you trust all these CAs. Okay? And the CAs, they issue certificates not for users, but mostly for websites. And so if you go to a website, you get a certificate by any of the CAs, hopefully one, on this public key of the web server, and this is how you trust the identity of the web server. But if you're not an expert and you don't click on stuff, you actually don't even know who you trust to say this, and it's very interesting, so you trust more or less the union, but if you go click on your browser, it's a very nice exercise to do this, you will find that there is about 600 companies that are all trusted, and they are from all over the world. And so by using a browser, you trust all of them. And of course, if you're paranoid like me, you can start deleting companies there, but most people don't even know where to find this list, right? And of course, there is a CA browser forum. They claim that at this moment, there is only 75 companies still in business. So there is still hundreds of keys there, where maybe this company is out of business, but their key is still there. Maybe some company has bought another company, whatever. It's a mess. But they claim it's like divided by 10. That's what's happening. It's a big mess. Running out of time, but more or less about 14 years ago, Leif Peters actually made a study. And then he found at that moment only 10 million websites started SSL interaction, about only half of those actually had valid certificates, and he found a big mess. So there was lots of problems. I will not go into them, but to give you one idea, there were certificates issued for the IP address 192.168.1.2, these kind of things, right? There was also an incident when you had 5 8-bit keys that could be factored in hours in 2010. Today it's in seconds. But also there's this famous bug in which Debian issued weak RSA keys, and these keys were still certified in these browsers by these CAs. They would never revoke them. Okay? So, of course, it's about usability. It's about revocation that's hard. It's about interoperability. So you can say, well, Firefox is going to make the rules tighter and kick out some CAs and impose some rules. And if they do that, then people switch to Chrome. But they have actually what has happened in part, right? So if you make the security too tight, then people go to the competition. And this is why security moves very slowly, only if all the browsers agree or if there is regulation. And then, of course, also there is many players. You think of the internet companies, the CAs, the users, but there is also producers of middle boxes that actually also have their say in what's happening, and the Cloudflares, and then the government agencies. So it's a very complex ecosystem. And if you read the Snowden documents, you can see that they love the complexity in PKI because they have special programs to go after PKIs, more or less, especially for the web. So I guess I don't have time to look at all the incidents, but there is Komodo issued a fake certificate. There is the famous DigiNotar incident, 10,000 of users in Iran affected. DigiNotar went out of business. And then the Turkish government, CA got caught issuing fake certificates. Bit9 lost their signing key. India, China, France, Symantec, Kazakhstan, and so on, and so on, and so on. So there is like, every year there is an incident of some of the CAs issuing fake certificates. Lenovo was, I think, the most interesting part. They actually issued a fake certificate for all Lenovo laptops in every browser. And the more interesting part is they also left a private key of the certificate on the laptop they sold to the users. So more or less, if you found this, you could actually attack any Lenovo user with a private key on this thing. I guess somebody never took the class of PKI in Lenovo. I guess that's the best explanation I can find for this. In the mobile world, it's not better. So there is an OS trust store and there is an app trust store. So it's very complex. In fact, there is not much research on this. There is a few academics that sometimes look at this, but more or less it's the same mess. So this Blue Box was this company published a very nice report, but I can't find them anymore. But again, the mobile ecosystem, you can, as an app developer, decide what you trust, or you can do it at the operating system level. And again, you trust hundreds and hundreds of players. So then after Snowden, Let's Encrypt came, 2015. So some academics and some companies and NGOs got together and they decided to offer free certificates. They said it's actually amazing that we have so few things encrypted because getting certificates is painful. So they actually tried to make it easier to get certificates and they were very successful. They also simplified the model. They issue very short-lived certificates and they don't do revocation. So at this moment they have more than 370 million certificates compared to the 10 million that were around 14 years ago. But of course, there is also 700 fake PayPal certificates. So if you register a website for PayPal where you replace the L by a 1, and you ask for a certificate from Let's Encrypt, you will get this. They don't do checking whether or not you're trying to phish somebody. They just say, if you have a website, we'll make a certificate for you, and you don't have to pay. So some people are upset with Let's Encrypt, but that's what they promised to do. So more than 80 or 90% of traffic is now encrypted. So the main merit they invented is the automatic certificate management environment. So they made it a lot easier to get certificates. More or less any student can now do it in an hour. Like, if you know how to set up a website, you can get your certificate very easily. They don't check who is the owner of the website, in the sense they don't check the company behind this. They actually check whether you own the DNS entry, or they actually ask you to put a certain file at a certain, via HTTP at a certain location. If you can do that, you claim to own the website or the address. And then they ask you to prove that you know the private key. But it's all automated. Europe actually wants something else, which is organizational validation. They want to know which company is behind this. And this has been tried also by the industry called extended validation. So more or less you try to figure out which business is behind this website. It's a very different function from who controls this domain. Now this is actually a mess, because take company ABC. Company ABC, if they're in Europe, they will have actually a BV in Belgium, they will have an Inc. in the UK, and they will have maybe something else in France. How do you know if you see ABC dot something in Austria that this company exists or not? So the idea that users can check this is actually absurd. And also extended validation, there the trick was then the browser windows becomes green. Of course, then the malware found out how to make a browser window green. It's not so hard to change some pixels on a screen, right? It seems to be not so difficult. And so extended validation died. So more or less the industry first said, give us money, we don't do anything. And then they came back with EV and said, give us a lot of more money, we're going to finally do what we promised to do. And then they said 10 years later, in fact, it doesn't work, we're going to stop doing it, we don't check it anymore. And now Europe comes and says, you have to do this. So this was eIDAS, and now eIDAS 2 approved a few weeks ago. So you have to actually put coax qualified website certificates in your browser if Europe tells you to do it. And even if the company fails the Firefox or Chrome qualification program, which is free, Europe can tell browser vendors to put in the keys of government CAs. And if they detect an incident, what does the law say now? Then the browser can temporarily suspend the certificate, and then the country involved will do an investigation. And if they decide there is no problem, then you have to put it back. It's kind of baffling. This was all introduced in the trilogue last summer. And so it's kind of shameless. Countries are in Europe using these quacks to actually potentially impersonate all user intercept connections. Well, in fact, what we need is Let's Encrypt. In fact, last month, finally the industry got together, the standardization bodies, and they wrote an RFC. This must have been on for a while. It more or less says, we're going to issue a special extension in certificates which says no revocation available. No, it's so difficult. You're going to have an extension which says don't even bother to look for revocation. If we set this extension, then you don't have to look for it. Okay, it's kind of the ultimate admission of defeat, or a new approach, short-lived certificates where you don't bother to revoke. So more or less they say the motivation is you have the short-lived certificate like Let's Encrypt, but you also have some producers issue certificates for devices. They issue a box, a webcam or something, they issue a certificate, and they never bother to revoke this, whatever. It's in there and you deal with it. And so I find it kind of interesting. It's not so surprising, right? If you look at what's happening in the field, it's just interesting that now IETF finally endorses this and says, look, it's now anyway, in so many cases, we don't do revocation that we can as well have a standard for it. So now you know that we're really in an interesting situation. Okay, so then after Snowden, people tried many things, and I'm running out of time here, so I'll try to be brief. I will not discuss them, but it's interesting that when many smart people got together and tried to fix things, and it kind of failed. Okay, all these things kind of never got traction. The only thing that actually works was done by Ben Laurie and Emilia Kasper, one of my old students, some other people at Google, called certificate transparency. And the idea is there, if you're going to issue fake certificates, more or less, so imagine that as a government of a country, you want to spoof your users, you force the CA to issue a certificate for Google, and now all the users will get a fake certificate for Google, and if they visit their Gmail, you will actually give them a fake site, and you can intercept the connection. Right? That's the model. The view of certificate transparency is, let's make all certificates issued public. That will stop governments from issuing fake certificates for Google. Because if you do this as a CA and you have to make it public, then you will probably not do this. Because then there is real hard evidence that you did this and that will refrain you from doing this. So their idea was to have a log, publicly visible, with a Merkle tree, where everything is hashed together, similar as what's being used in cryptocurrencies. And so it's append only, and so you can check presence of a certificate very easily with a path. So if you want to check X3, you just need those 3 values. In general, even if there is a million certificates, you only need 20 values to check. So very simple concept. And the idea is to sign this with the log ID and a timestamp once per day. Okay, now of course that's not good enough, because if I'm going to issue a fake certificate for Google, I will do that at 7 in the morning, and I will impersonate, spoof my users between 7 and 9, and then I will make it disappear again. Right? So you actually have to, you can't wait 24 hours to check, has it now been included? Because in this model, it's only every 24 hours that you update your public directory. And that leaves a gap that's enough to attack. So they actually came up with a very clever solution, which is that if you submit a certificate, you actually get a signed certificate timestamp, so the log server will say, yes, you submit your certificate, and we're going to include you. Okay? Now, there is a chicken or egg problem here, because this certificate should be included in the certificate. This is SET, so it should be included in the certificate to prove that you actually got it. So there is a clever bypass for this. So what you do is, in your certificate, you actually put a dummy field, so that the certificate actually breaks in a critical extension called the poison. And this certificate you submit, for this you get the SCT, and then you put this SCT in the place of this poison, and that's your new certificate. And anybody can check that those 2 certificates are similar except for the poison field. So it's a bit of a clever trick to kind of have the solve the chicken and egg problem. But so, and again, these SETs can be stapled together with OCSP. This is cool. Of course, you need to have volunteers who want to run these logs. These logs, of course, are enormous, and they have a lot of demands for it. And you need some players to check those logs. But I think it's a very nice system. And again, something that made many people very upset. So you're upset. Browser vendors cannot impose additional checks like certificate transparency unless they're European standards. And the Europeans will decide whether or not this is allowed or not. And we made a lot of noise about this, and there the language has been changed a bit. So now Europe has said, yeah, well, it's okay, and in fact, you may want to do it, and of course, but so again, more or less, the IDAS regulation could be read as, and if you're going to do these kind of things to protect yourself, we'll make it illegal. So it's really, this is where the battle about the internet is being fought. So I guess the other problem is user interface. The average user doesn't understand this stuff. So time to wrap up. So PKI seems very simple, but as you see, it's actually very complex. That's an important takeaway. It's a success because we have now 6 or 7 billion EMV cards. We have now close to 400 billion certificates on the web. There is many other ecosystems that have certificates and PKI. But because it's so important, it also means that governments go after it and try to undermine it. There is never going to be a global PKI. You cannot imagine that the financial sector uses the same models as the internet, the Wild West. And revocation is always hard. I think this is an old slide, and I guess it's so hard that, in fact, in some cases, we just give up on it. Of course, that sounds very easy because now your system is cheaper, but you have to think of the consequences, right? This means that if you issue a Let's Encrypt certificate, or you get a Let's Encrypt certificate on your website, and the next day your website is hacked, well, for 3 months, the certificate will be valid, and there is nobody who takes any responsibility. So it's up to you to shut down your website now for 3 months. So this kind of no revocation euphoria is also a bit dangerous, right? So you probably have to go to much shorter certificate issuances, maybe hours or so, because I think that there is 2 reasons why this thing is complex. I think first, the world is complex, and you hit with PKI the real world, how you write names, who owns a name, who owns a website, who owns a company. These are the real issues which are actually very hard in the real world as well, and you can't just replace it by cryptography. And then, of course, the other hand, the whole system was conceived in the 70s when everything was offline, and now we're online. If you would redesign it, you probably would do something completely different, but I guess that's too late. Okay, sorry for running it over time. We're going to stop here. Thank you very much for your attention. Enjoy your coffee break.